can record, yeah.
Yeah, I'm recording.
Okay.
Okay, so let me share my screen. So, okay. So can you see my screen? Which is just a note. And so basically we're planning to do 3 quick demos, one for the ISET, and the other one for Abacus ISET, and then next for MATLAB ISET for the shell coupling. And here are some notes for me, and I can, there are also some noteworthy points. Maybe I can send you guys this brief file to you guys for future references. So let me, first we look at the ISET coupling for solid models and choosing this T-joint example with a static crack. And so you can see the folder directory, right? So basically, let me, maybe here, it's okay. So basically we have a couple of test files to run this IGL simulation. So we have 2 TCL file. One is to do the global solution. And the other one is to do the IGL local solution, and which in this case, we do a GFAM global local analysis in using this TCL file, right? And then, but if you want to solve some other problems, basically you can choose your own method in this global and this this method, this GFAM local TCL file. And for this case, we have 3 GRF files. One, it is the global model, this one, and the other 2 is the mesoscale model and the local model that is used to run the GFAM global local. And we also have a crack, so we have a CR file here. So
just a quick question, Haoyang. For the local problem, you have your own GRF. But you also implemented the capability of creating the local problem from the global problem, even when the global is a hex mesh using something that was originally developed by Patrick, right? Is that
that is checked in the master, or in a repository. So
just again for maybe Nathan and Javier that are not very familiar with these things. You can, instead of create a GRF for the local problem, you can create like a bounding box and say my local problem will be based on these elements inside of this bounding box. So even if the elements in the global problem are hexes, you create tests in the local problem, white tests, well, because we want tests to use with the crack manager.
Yeah, that's correct.
Yeah, so they because not need to create the local problem mesh.
Yeah.
Okay.
Yeah, basically, currently we have 3 ways to, or I mean, 3 ways to create a local problem. One is to basically, if the global problem is a TET mesh, we can just create a local problem using like out of that TET global mesh, like which is just a copy of that region of the mesh. And the second way is if the global mesh is a hex, then as Professor mentioned, just mentioned, and we can use the algorithm to subdivide the hexes into 6 or 5 TETs and create a TET mesh out of those hex mesh. And the third way is the way I do here, is just to create a local mesh GR file and read in that local mesh file. Yeah.
Does this way makes any check to see if the meshes are conforming?
No,
or it's assumed?
It does not. So basically, if it's not, so what we need, the user needs to ensure is that the local mesh is nested in the global mesh. And I don't think the code checks that. And if it's not nested, and you will find out because the boundary conditions of the local problem won't be applied properly. So,
Okay.
yeah.
Mm-hmm.
Okay, so let's see.
Yeah,
so
this way that Haoyang explained that he's using, it gives more flexibility. Let's say you can have, let's say, a hole in the local problem and no holes in the mesoscale problem, like in the example from chapter 5. So the geometry can be different, but the user needs to make sure that the local mesh is nested in the mesoscale mesh.
Yeah.
Okay.
So when the geometry is the same, then it's more convenient using the other two approaches.
Yeah.
Okay.
From the user point of view.
Yeah.
And
also, if you use the hex to tet conversion method in the, so a prerequisite is that you need to have a good hexahedral mesh, because for example, for the, if you have a hexes mesh with poor aspect ratios, you will probably not want to use that hex to tet converter. Because if you have a thin layer of hexes, and that will divide it into 6 or 5 tets, and those tet aspect ratios won't be good for your solution. Yeah. Okay, so yeah, so those are the files you need to run the tests, and then I just basically run. So the mesoscale TCL file is basically the driver of this IGL solution analysis. So basically, you just type ISET and to run this mesoscale TCL file. Because, and then what we can do is that we can look at this. Is this a bit small for you guys to see the?
No, I can see it very well.
I can see.
Yeah. It's fine for me.
Okay. Maybe you can. Okay, let's just leave that like that. So we can take a look at this mesoscale TCL file, and in the beginning, just a bunch of parameters for the file names, and then we start this analysis. We set the enrichment orders and set the GFEM global local iterations. So just the normal things, like what you would set up before you run a GFEM global local analysis. And starting from here, you can see, so inside this mesoscale TCL, we call another ISET to run the global TCL before solving the mesoscale problem. So basically here is execute the ISET and the global TCL file, and it saves the output to a output file. And then, so while this is running in the background, we just wait for a few seconds, because after this is done, it will generate like a temporary file. Is called the interface data available. And if this one is available in this directory, which means that this global solution is finished, then we can proceed the following analysis in this mesoscale. So after the global solution is finished, then in this mesoscale, what we do, so basically, So the IGL algorithm commands are things like this. So basically, I have created this TCL command called IGL algorithm, and to use that, you first need to create that. And then the first thing you want to do is to read in the global interface data to basically assign the boundary conditions to your mesoscale model. So this is what this command do. And after, so this one is assigning the mesoscale BCs. After this is done, and we can solve the mesoscale model as usual.
When you set BCs like this, is just point BCs, or can you do like face BCs too?
This is point BCs, yeah.
Okay.
Point Dirichlet BCs, yeah.
Point Dirichlet, okay.
And after this point, so basically, these are the two IGL TCL command you need to run before running this mesoscale model. After this, you just do the GFEM global local as usual to solve this mesoscale and local problem.
Which variable is that you're passing the interface data, Haoyang? What's the value?
Is it the name of the file?
This one, yeah, it's the name of the file, and it's yeah. For this example, I set it up at the beginning. It's just called. It's just the name of this example appended by an interface data. Yeah, you can choose your own file name, but it's more organized this way, I think.
Okay.
So yeah, so then you just solve this GFEM global local. You just perform this GFEM global local analysis as usual. And basically first you solve the initial global problem and you start solving the local problems. And here I'm creating a local problem from a file and then passing in this file name and to generate the local problem. And I do some mesh refinement, and I do...
Just a quick thing. Are we using Spring boundary conditions for the local problem?
I normally use Spring boundary conditions to... You can also use displacement boundary conditions as well. But I find for my problem, yeah, your Spring local problem, it's more accurate as I do GFEM global local iterations. So it converges faster than the displacement boundary conditions. Yeah. Yeah, so basically in the local problem, we include this crack, right? So you guys should be familiar with the crack, how to set up that. And so just a bunch of parameters and to process the crack. And after solving these local problems, and you solve the enriched global problem. And you solve the enriched global problem, and then here in this for loop, I do the GFEM global local iterations. Yeah. And just extract the stress intensity factors. And after this, here, so this one is the command you need to run after each GFEM global local solution. So this is GFEM IGL algorithm, and it basically computes the interface residual forces based on the GFEM global local solution. And in dump, it writes the data to this file. And also the acceleration technique is applied while running this command. So basically here, you need to specify which acceleration technique you want. So what we have is the no acceleration and dynamic relaxation. And one thing you need to know that is, so even if you use the dynamic relaxation, the first time you call this function, you need to use no acceleration, because the dynamic relaxation cannot be cannot compute the beta at the first IGL, at the first step.
Because you need the data from the previous
because
solution.
you need because you need the data from the previous solution. So basically the first one, you just specify no acceleration, but later at each IGL iteration, you type just dynamic relaxation. You will see later. Yeah.
Okay.
So basically after computing these residual forces and write it to an interface force file, and here we also get the norm of the residual force for the IGL analysis to set our initial residual, because our convergence criterion is to examine the relative norm of residual at each iteration. So we need to get the initial residual. Okay, so then up to this point, it means that the first IGL global and local solve is finished, and we have this interface residual force that can be applied to our global model. So we just create a template file calling this interface res force is available. This
when you do exact touch, it creates this file.
Yeah, you do touch, it just create a file. It's just an empty file. Yeah.
That's a Unix command.
Yeah.
It's like a terminal thing.
Right. Exec, you execute whatever you pass on the terminal.
Okay.
Yeah.
Exec is a TCL command, but after that, you just execute that in the terminal.
Okay, that's useful.
Yeah, because problem here, you can, because in the global file, we check if this interface residual force is available. If it's not, then
you wait.
Yeah. But let's just finish looking at this mesoscale TCL first. So after this, we have the initial residual, and we can start doing our IGL iterations. And so here I set the maximum number of iterations for IGL is 10, and I can set the convergence criterion. I use 2 of them, but usually just one of them will be satisfied. So one is the relative residual, the tolerance for the relative residual, which is e to the -5, and the other one is the absolute residual, meaning that if your residual is really small, we can just stop this iteration. So the first if condition just check if this absolute tolerance is satisfied, and this else condition is just if the absolute tolerance is not satisfied, we just keep doing this IGL iterations until this relative tolerance convergence criterion is satisfied. Okay, so, but here, one thing to notice that because we have this interface data available is like as a flag to tell that if the global solution is finished, so it will be generated after each global solution, but before each iteration, we need to delete that, right? Otherwise, it will just send a false signal to this, to this while condition. So we first delete this this interface data available file, and we solve this global problem. And then we wait until this file is generated, meaning that the IGL global solution is finished, and then we carry on to the next IGL mesoscale solution. Okay, and then basically the overall procedure is the same, and then we call this IGL algorithm to read in this interface data to set the point BCs to our mesoscale model, and then we solve the enriched global, and we do this GFEM global local iterations. Yeah, and then we extract the stress intensity factors. And here, so as I mentioned, the first time we call this IGL algorithm compute and dump interface residual force, we use no acceleration because we can't use dynamic relaxation for iteration 0. And here, if you want to use dynamic relaxation, you just specify dynamic relaxation here. And it will just use that algorithm. And if you don't want to use acceleration, you can use this command and use this argument to not using any acceleration technique. Yeah.
Haoyang, remind me, what's the residual? How is it calculated? Is what minus what? Is the reactions?
So the residual is the reactions. So it's basically the nodal reactions on that minus the whatever load you applied on that node.
Okay. Okay, so nodal reactions minus what you applied. Then it should be 0. Okay.
Where reaction is
at the interface.
Yeah.
Right.
Okay.
Yeah.
And that's the difference between the force that the global problem exerts on the node minus the force that the mesoscale exerts on the node. Is that correct, Haoyang?
Yeah.
Okay.
So in the global problem, we need to find the global mesh should have elements sharing a node.
Yeah,
Some
we
elements,
have elements sharing the node.
Some elements are, let's say, outside of the mesoscale domain. Some are inside of the mesoscale domain. But that mesoscale domain in global problem, we don't want those. Those are kind of, I don't know how we call it, complementary element area.
Yeah, complementary area.
Yeah, or complement subdomain. So that's what we want to replace with the mesoscale model. But we don't do that, right? So it's there. So when computing the forces at that node, you compute contributions from the elements sharing that node, but only from the elements that are not in the complementary area.
Yeah, basically, if you look at this problem and then, so I'm showing this. This is the global. And this is the global model, and this is the mesoscale model where we have included this the fillet weld, and then and so basically here is the interface, and along this surface we have an interface. Along this surface we have interface nodes, and the residual is that we compute the nodal reactions on this mesoscale nodes at the interface and subtract that with those the reaction force from the global model, but it is for the element inside this complementary region. So basically the global element inside this bluish purple region to compute the global reaction force. And we subtract that with the mesoscale reaction force to get the residual to drive our IGL iteration.
Yeah, I saw that you have a function to find the elements on the interface in the IGL algorithm class, and those elements are used to compute those reactions then.
Those elements are actually, we need to identify or specify those elements in the IGL global TCL file. So I will talk about that.
Okay, I'm skipping ahead.
Yeah. Okay, right. So here in this mesoscale model, we just do a dynamic relaxation, and then we get the current residual, and we check the residual here in the TCL. So basically, we can compute the relative residual, and then if it's converged, it will just stop the simulation.
So Haoyang, this assemble and solve on line 306, this is for the mesoscale problem?
Yeah, this is for the mesoscale problem.
So you get new loads, new BCs, right, from the global problem. And now you want to apply those new displacement BCs on the mesoscale.
Yeah.
And then you solve it. Is that what you are doing here?
Yeah.
Okay. Because in theory, not that we are going to do this, but we don't need actually to assemble and solve again, because you only change the boundary conditions, right?
Yeah. That's true. Yeah.
Okay. Well, we are changing the values of the described displacement.
for the mesoscale, yeah, that's true. And then we also, but we still need to resolve assemble and solve the local problem.
Yeah, that we need, yes.
Yeah, that we need, yeah.
So when you do this first assemble solve in the middle of the iterations, does it know not to use the local problem shape functions? And like the one in 306, when you're doing that assemble, and considering that you're doing this over many iterations, you already have a local problem there. The code knows not to use the local shape function of this local problem in this assemble from 306, and only use it in the enriched global problem in the assemble after line 327.
No, actually it uses that local shape functions.
It uses from the previous step.
Yeah, from the previous step.
Okay.
And then you need to do global local iterations to to get a better solution.
Okay.
Yeah, I've never tried, but actually I think maybe you can try just to delete those special bases while doing this assemble and solve to see how it happens, how it works. Maybe I think there might be a TCL command you can just not using the special bases. I don't remember.
Yeah, I was even thinking that maybe the local shape functions from the previous step might be something better for this one to compute the PCs for a local problem of this step.
Yeah.
I don't know.
Yeah, that's a good
point. Okay.
Okay, so basically this is the workflow for this mesoscale TCL command, TCL scripts. And there's only a few things I want to mention in this global TCL file. Basically, so this global TCL file, as we just saw, it is called inside this mesoscale TCL, and then so this global TCL is just solving the IGL global problem, and it will apply the residual forces to our global model along those interface nodes of the global model to update our global solution, right? And then, so one thing I want to mention here is that on this line 67 in the IGL algorithm, and we set element list local command, and there's a bounding box which is actually telling this solver to identify the global elements that inside this complementary domain. So basically, we need the solver needs to know which side of the element to use to compute the reaction force of the global model. Does that make sense? Oh, sorry. I can't hear you.
Picking on sorry, I was muted.
Okay.
You're picking all the elements from the global GRF that are inside of the mesoscale domain.
Are inside of the domain of interest in this mesoscale domain.
Just a quick question: if the elements are conforming, so you have to do this bounding box a little bit bigger, no? Than the mesoscale to avoid float comparison errors, maybe.
How do you
so the bounding box, it works that so the bounding box will so this bounding box will get all the elements that touches the bounding box. So basically, if you look at the bounding box, it's basically a little bit smaller than this region. Right. So so if the element has a node in this bounding box, so this element will be included in this selection.
Yeah. Okay. I understand how this bounding box works.
But actually, so I'm just using one bounding box here to get all the global element inside its domain of interest. But in fact, it's just a list of elements that if you look at the code to search in this IGL algorithm. So basically, we just need to tell the code which side of the element to use while computing the reaction forces of this node, for example. So the code needs to use this element instead of this element, instead of adding contribution from this element. So basically, in this element list, we can actually just add this row of element and this row of element and this row of element that touching the one side of the interface.
So you don't need all of them, right? So
we don't need all of them because imagine if you have another example and have a multiple this mesoscale domains, and you can just set a list of elements that is on the right side of this interface. Yeah.
Okay. I understand.
Yeah, but this just figure that using one bounding box is cleaner. Yeah. Yeah, and at the end of this global TCL, we just compute and dump interface data, and so this one will contains the global solution on the interface nodes, and then we just use a touch to tell the mesoscale TCL that this interface data is available.
Okay. What about the first interface data, the interface res force data available? Because there's no interface residual forces in the beginning of it all.
Yeah, there's no, and then we just it does not exist. It will skip this line. It will just solve the global problem without any residual force. Yeah, just the initial IGL global problem is just there's no residual force applied to it.
It's just the actual load, right? The real load.
It's just, yeah, just the real load, yeah.
Understood.
Yeah, starting from the iteration 1, and we'll have this file, and we can read in this residual force and update our global solution.
Cool.
I think it would be good if you can show us the open these files. I think you have two files, one with displacement BC, the other one with forces, right? Residual forces. So you can see the syntax in those files.
Yeah. So I've already run this one. So this is the. So this interface data.dat is generated from this global T-cell file. So it's basically the global solution, but the quantity it contains is the interface node ID and the number of degrees of freedoms, and this solution displacement of this node and the reaction forces. So they're basically 8 entries for one line. So it's the node ID, number of degrees of freedom, and 3 entries for the displacement, and 3 entries for the reaction forces in 3 directions.
Do we need the reaction forces in this file? Well, I thought we only calculated displacements.
We need that to, because we compute the residuals while running this mesoscale model. So the mesoscale model need to get this global reaction forces and to to subtract that from the mesoscale reaction forces.
Okay. So that's not the residual, that's the reaction force, right?
That is the reaction forces of the,
Yeah, that's a reaction force from the complementary area, right? Complementary domain.
Yeah. Yeah, so so in this mesoscale model, it's reading this interface data.dat file using this command, and it will use the displacement data to assign this points, usually BCs, and it will also store these reaction forces from the global solution for later computation of the residual forces along the interface. And then when we call this function, the compute and dump interface residual forces in this mesoscale model, and it will basically generate this file, the interface resforce.data. And this is the residual forces that we use to update our global model. It's just again the node ID, number of degrees of freedoms, and the residual forces that to be applied to our global model in the next iteration.
And these reaction forces are already accelerated or not?
Yeah, this is already accelerated or not. Yeah.
Okay.
Okay, so basically that is how it works. So if you run the ISET of this T-cell command, it will just run the whole simulation and stop when it converts or it reaches the maximum iteration number you specified. And yeah, eventually you will have your solution files, the VTU files you want. Yeah.
So in the GRF files that you use 3 of them?
Oh yeah. There are. I'm sorry.
You also need some interface data. What's the
that's
additional data that I need when solving?
Yeah, that I need to mention. So here in both the global GR file and the mesoscale GR file, we need some additional problem data to map between the local interface node and global interface node.
Okay.
So let's look at this. Sorry. where's the? So let's look at this global. This is the global GR file, and the user need to specify this problem data section with this keywords called local interface node. And this 156 is this global node number. And
so it's local of the IGL, but it's really the mesoscale in our method, right?
Yeah, it's local in terms of the IGL, but in this case, it's the mesoscale model.
Okay.
Yeah.
So the 159 is the number.
So
sorry, you can go.
Is the global node ID in this file, and this node ID equal to 311 is the mesoscale node ID that this global node is corresponds to. So we can basically check this one. So 159. We can see here.
Okay.
159 is -6, -2, and 0. And this is a mesoscale GR file, and we are looking for 311. So the -6, -2, and 0. So they are they're the same they're the corresponding interface node. And usually what I use to generate this interface, this problem data for this local interface node is just, I think sometimes I just use Excels to, basically you can copy in those coordinates of the global and local nodes, and you can sort them and match them along the interface. And to get those numbers that you can copy to here. I thought maybe I had a script, but I couldn't find it now. I have a script to generate this matching nodes. But
a script that you read the two GRFs.
Yeah.
You read the two GRFs and
you just read two GR files of the node section and get those nodes with the same coordinate systems. Yeah.
Okay, but you want to match you only need interface.
Yeah,
so it has to be nodes that are on the has to be nodes that are on the boundary of the mesoscale only.
Yeah, for a regular domain, you just need to know. Basically, for this one, I know the interface is at x equal to -6 and x equal to plus 6, and then I can just search in those. I can sort those coordinates and find those on that x coordinate. Yeah.
But in the general case, we will need to find a way to identify the interface. So to match nodes on the interface only, because we also have matching nodes inside of the mesoscale.
Yeah, that's true.
You don't want those.
Okay. A way to do that is maybe if you generate a model in a general case, if you generate a complicated model in Abacus, then you can manually select those nodes, right? So, or you have an interface, you can define a surface that which is basically the interfacing. Then you can get a selection of nodes along that interface, and then you can get those node numbers. Yeah.
And you can dump from Abacus to a file. Let's
say. You can if you have you can define groups of nodes, multiple group of nodes in Abacus, and then if you save those nodes with a name like interface nodes, and when you generate the input file, it will be in that input file with the node ID.
I see. Yeah, that will be very helpful.
Yeah, so basically in this global GR file, we specify this local interface nodes. And on the other hand, in this mesoscale GR file, we also have this problem data section. We specify this global interface node, which is basically in converse, right? So there's 311 and corresponding to global node 159.
If they are the inverse, why do you need to set both?
Because they because
it's different instances of ISET running.
Because they don't, the mesoscale T cell doesn't know the global model, and the global model doesn't know the mesoscale model. The only data in transfer is this .dat file, and this .dat file, if it's generated from the global model, the node ID is the global node ID, right? And this residual force data. So this is the mesoscale node ID. So we need some like information between those two models to set up in this GR file.
Yeah, I'm not sure if it is better or just thinking that maybe one could send to the other through this interface data file instead of setting in two places. But
this is possible for ISET, but if you use Abacus, maybe it's harder.
Okay. Yeah, I can see that.
Okay. So yeah, that is basically in order to run this IGL, there's some IGL command you need to know in this T cell file, and also in the GR file, we need this global and local interface node problem data.
Okay.
Okay. So this is pretty much what, and the local GR file is just as normal. There's no need to change anything or add anything there in the local GR file. And so yeah, I think this is, it's important just to understand this IGL coupling with ISET, because with Abacus ISET and MATLAB ISET, pretty much the same idea with a few noteworthy points, right? So is there any questions you guys have right now?
Right now, no.
Not really.
Okay.
So this is from one of the problems in your dissertation, Haoyang? Because I don't know if there's a static problem there for the T-joint.
No, actually, so this is just a simpler one. It's a static crack. And in my dissertation, it's a propagating crack, but that file is super long because with global local with crack propagation, it's kind of complicated.
So it would be good if you can share this with us later on.
Sure, I can share this.
Well, at the end, when we go over the other tutorial problems.
Sure. Okay. Okay, so next is the Abacus and ISET coupling, and then basically the same example. And then we are looking at so the Abacus and ISET coupling, so there are basically a couple of files we need to run the examples. I forgot to do this, but I can do this. Global mesoscale local. Okay. Sorry. So these are the files we need to run the abacus and ISET coupling with the IGL. And again, we have pretty much the same, the mesoscale TCL file. And then the global model is driven by this abacus.int file. And then there are a bunch of abacus script to do the conversion between abacus quantities and abacus files and ISET data files. But I will talk about that later. And so let's just take a quick look at this mesoscale TCL file and follow this the steps. So this is basically the same as before with ISET coupling. And the one thing we need to change here is actually, instead of calling ISET to run that global TCL, we just call this abacus to call this execute abacus.py to run our global model. And the abacus job file name is set here as an environmental variable, but because this Python file takes this environmental variable to run the abacus simulation.
And this is abacus.py is a file you created.
Yeah, this is file you need in this folder to run. It is developed based on some old abacus ISET coupling, but I need to add some extra code in this to run IGL simulation.
Yeah, I think this was start with Geronimo, then
yeah,
Yush, and then Julia, right?
And Julia, yeah.
Oh wow.
For the based on stat condensation, the coupling.
It's a file that has history.
Basically, yeah. Before running this abacus directives, then we need to set two environment variables. One is abacus job name, the other one I call is abacus conversion mode. And conversion mode is called IGL, right? And so here in this execute abacus.py, so if the conversion mode IGL, it just set this mode parameter to 2, and it will be passed in to some later Python functions. And the job name is, the job name is got from this environment variable abacus job name that we set in this TCL file.
Cool.
So basically, this TCL file is calling this abacus command to run this global model, and this Python script is running the global model on this line. And then if the job is submitted and it's finished, and then this Python script will call another function in this module, which is abacus converter function abacus to ISET, which pretty much converts abacus quantities along the interface to ISET data format.
And it's in binary, right? It says there. Those are binary format.
See. No,
Focus
for now it's not.
100.
Yeah,
False. Okay.
Yeah, binary is false. Yeah. So you.
Okay.
I don't think. I think you can try, but I set it to file because you can take a look at those files and to see if those data it makes sense, right?
This Abacus converter object is a class that we have. Oh, it's a file that you're opening. Right?
Yeah, it's basically we have three scripts. One is the active Abacus, which is the main driver of the Abacus global solution, and then it uses this Abacus converter class .py. And then we have an ISET to abacus.py, which is later we convert our ISET residual forces to abacus load.lod file. Yeah. So get back to this abacus converter and abacus to ISET conversion, and it basically converts the interface data from the global solution, Abacus global solution to ISET's data.
And you had previously set the interface using that bounding box. This time you said that in Abacus when you created the model.
This one we need in Abacus model .input file. We also need to set those elements and interface node. So if we look at this int file. So this int file is set in this way, but in this way, because you see I have this int file, but I also have this .elm and .node and .load. So .elm is the element list, and .node is the nodal coordinates of all the global in the global model. But basically you can copy, when you generate an Abacus int file, you will have everything here inside this int file. But I just separate them to a separate file, which looks a bit more cleaner, because otherwise it's going to be too long for this int file. But you can see, so in the nodal coordinate section, we use this .node file as input. And for this element connectivity section, we use this .elm file as input. So basically it defines the nodes and elements. And then this is the materials. And then what's important is right here. So this is the element site. So we need to create element set. It is called element equal to local. So these are basically the global elements in this Abacus model that inside those complementary region.
All of them, or only those that are next to the interface?
This is all of them, but you can set those. So this works the same way, but you can only specify those along the interface on the inside of the interface.
Okay.
And these are, so basically we need to have this section called element set. Now element set equal to local and the element IDs. And next, we also need to define another section called inset. It's node set. It's inset equal to interface. And these are the global interface nodes. However, I think, let's see. Yeah, so these are the global interface nodes.
And you generated this in Abacus itself or using Excel? How did you do that?
The elements that all these element set and EL set and N set are generate those in Abacus. So when you can select those nodes or elements in Abacus and create a set.
Okay.
And then in the global problem, when you calculate the reactions, you said that you only use the elements that are in the inside part, in the complementary part, or in this L set equals to local. Abacus knows how to do that. Compute
Yeah, when you
reactions only
have,
those elements.
Yeah, when you have this element set equal to local, and at the end of the elements, at end of this Abacus int file, so here on these two lines. So basically, for element output, I only use this local element set to compute these nodal forces. So basically, so this line will tell the Abacus to use this element set to compute the nodal forces, not using other elements outside the interface. Yeah.
Okay.
Very useful. That's exactly what.
Yes. So this is basically, so besides these two, so besides this element set and nodal set, you need to specify in this input file, and you also need these two lines. So basically, this one is to compute the nodal displacement along the interface,
which will be directly boundary conditions for the mesoscale, right?
Yeah, which is a directly boundary condition for the mesoscale, and this one is the nodal reaction forces.
Just that you need to compute the residual.
Yeah. That we need to compute residual, and after this point is basically works the same way as a coupling. But one thing you need to remember is that in this IGL GFM global local and global.imp, we can only post-process this. You can't post-process anything else because the current way this converter works, it won't distinguish different set of element or set of nodes. So basically, so the post-processing of this int file will not give you the full solution of this global problem, because this converter will just search for this field called U and also this field called N4 to do the conversion. And a workaround is that I have another file called this IGL GFM global local post processing, and basically everything is the same, and then in the end you can post process without specifying element or node set. So basically this will give you the full solution on the whole global domain, and you can specify any like fields you want to post process, like U and nodal forces, stresses, or mixed stresses, or if you're doing a nonlinear analysis, you can have only plastic strain and stress here. But when you do this IGL analysis in this .int file, you cannot post process other quantities.
So then you are solving the problem twice?
So I solved this. So I solved it once, but for this post process, I mean, I only run this post process.imp at the end of the IGL. So after everything is finished, right? So I only care about the final solution of this global, of this global model.
So imp, I'm not familiar with Abacus. The imp is something that you call from Abacus after you solve the problem?
Yeah, so this is basically the job name. So I set this Abacus job name equal to IGL GFM global local global, and it will set this job name here, passing as a parameter to run this Abacus command. And so basically this execute abacus.py is calling this imp. And at the end of this simulation, I'm just post-processing for the final IGL global solution and passing in this post-process.imp file to get the full solution of the global. Yeah.
So only at the very end that you call this one that you you have the whole solution, the whole domain, not just the interface. Okay.
Yeah, that is something I want to note here.
So it's not possible in the same imp dump different sets. One like you specify, and the other one that's the whole thing.
I think that requires some improvement in this abacus converter. I think because it takes the ODB and they search for. Right now, it only search for the field name. So for you or for nfork, it does not distinguish between different element or node sets. So basically, I think there might be some Python functions or parameter you can pass in to check if this is the element set or node set you want to post process.
Okay.
Yeah.
Okay. Well, that's something that we can, if needed, we can do later on.
Yeah. Yeah, right. So that's finished. So basically that is all I want to talk about for this .int file. But when we look back in this .tcl file for the mesoscale model, and so the only difference between this one and ISET coupling is that we set up this abacus jobs and we calling this abacus command to run the global model, and everything else is the same. So these are the same command, and after running this GFEM global local, this command is also the same as before to compute the residual forces from the based on the global reaction and the mesoscale reaction forces. And the iteration is done the same. And
that's good. But then after you have it work in ISET, moving to ISET abacus is straightforward.
Yeah. So one thing is that, remember previously when running abacus in FA workstation, we need to queue some handling process of abacus using some command. It does not need it on my office machine, but if you need, you probably need to use this command to queue that, because we activate or we run abacus at each iterations, and then if it's hanging there, you cannot. It will just stuck there. It won't run the following iterations. Yeah, so this is what you need to do, but maybe they fixed this issue now. Yeah, I don't know. But so again, so it's basically the same setup in the. Okay, so I forgot this one. So after each GFEM global local solution, we get the residual forces, and then we need to call this Python script. I created this called ISET to abacus.py to write our residual forces into this abacus.load.lod file format. And this .lod will be fed into the abacus int file here as an input to update our global solution.
So Haoyang, this imp file, you're generating abacus and then you add those last lines by yourself?
Yeah.
Okay. Sounds good.
One thing about this .lod file is that because this int file, so it will always process this line from the beginning, even for the initial IGL. So you need to have this file at the beginning. So basically you need to have, this, let's see, you can take a look at this file. So this is called cload the concentrated load, and then the node ID, the DOF, and the residual force. And so for the initial step, we need to have this file, but with all the entries equal to 0.
Okay.
So what I do is I always keep this, I have this res force initial dot LOD equal to 0. This is for the initial one, but because so I need to mention this because I have this script to set up this test. So do a little bit of configuration of the test. Basically, I just need to copy this initial dot load into this interface res force dot load, and I'm removing some output files and data files from a previous run, and just to make this directly more cleaner. And the important one is that we need to have interface res force dot load file prepared before running this this global.int. And in that file, we need to have those entries equal to 0 for the first iteration. But after that, after each iteration, it will override this .load file with the new residual forces. Yeah. Yeah. So that's basically it for the ISET to Abacus coupling. So basically, we have the 3 Abacus Python scripts, and we have the mesoscale TCL file to do the global local, and we have this abacus.int file to run the global model. And we also have this postprocess.int file just to get the full solution of the global model after the analysis finished. And these Elm and .node files, you can have those, or you may just put them, the element and nodal informations into this int file as you wish. So yeah, another thing I want to mention for Abacus asset coupling is that for my simulates, for my work, I found this ODB to VTK converter online, which basically
I was going to ask you about that.
Yeah,
because you show the pictures in Paraview, right?
Yeah, because you want to show them, so the global and mesoscale models together in Paraview. Otherwise, one is in Abacus, the other one's in Paraview. It's hard to visualize those or to generate the figures. So this I found on the internet, and it works, but it's not very robust. But they have this user guide you can follow, but it's pretty simple to use. And this is the file I generated based on this post-process ODB file, the VTU. And I can show that
yeah, maybe that converter can go to set solver tools or something like this.
So that so you can see, so this is the file I converted from the ODB file. And so these are the file generated from the GIF to ISET, and it's the deformed configuration, and it basically converts well, and you can see the displacement, you can see the stress components. But one thing I want to mention that so these two, so they only have, initially they only have this ODB to VTK.py. So to use that, you need to copy this .py into this Abacus Python library in your machine. And then on the and then on your machine, you basically, maybe we can take a look at this guide they compiled. Yeah. Yeah, so to use this ODB to vtk.py, first you need to copy this one to the directory of the Python lib of abacus somewhere on your machine or on the workstation. And then you type abacus space Python. It will invoke the abacus Python Python script. So you can run any abacus Python lib functions in this environment, and you import this ODB to VTK library, and then basically in that library there's this function called convert ODB to VTK, and you specify the file name you want to convert here. To do the conversion. But this .py only works for single precision. So if you run your abacus in a double precision, so the Python, so I modify this file to be able to run, to be able to convert double precision of DB files. But I will check this folder in for you to use. But I mean, maybe there's some better. So I found this 2 or 3 years ago. Maybe there's some better converters on the internet you can find right now. But I say it is not very robust because if we look at this ODB to vtk.py, you will notice that it will grab the field's outputs based on the keywords, and but it's not checking if that fields exist. So basically, if you didn't post-process those fields, so this Python script will just crash. So so this is how they implemented this. So basically what I do is I know I post-process the displacement and stress, and then I just comment out all the other fields. So there's so if you have some other fields you want to convert, you can uncomment those, but you need to make sure in your abacus abacus.imp, these are the keywords and fields you post processed. Okay, so that's the converter from the ODB to VDK. So I can also check those in if you want to use that. And you can also search on the internet if there are some other better solutions to this.
Yeah, that sounds good.
Yeah, if you can just share those files, we don't know where they're going to check in at this time, but just to make it available to Nathan and Javier.
I just Google abacus to Paraview, and that was the first link that showed up, the one that you showed.
Yeah,
it's pretty famous.
Really, but they yeah, it's been a while. They compiled this file 5
Maybe
years
they have an updated version.
Maybe, maybe they updated their Git repository. You can check if they have improved their code. Yeah. Okay. So yeah, that's all I want to talk about for Abacus ISET, because everything else is the same. For example, in the mesoscale GR file, you also need to specify those interface node ID. Yeah, for the code to work. Yeah, so this is the same idea.
Okay.
Okay.
Looks good.
So last is the MATLAB and ISET. So this one, I choose this cantilever plate problem, which is simpler. And so basically what we need is a TCL file to run the mesoscale model and the MATLAB script to run the global model, and a bunch of MATLAB codes to support the shell solution. And so this is based on that MATFAM code for the shell. I think I modified two classes. One is compute residual forces. The other one is this one. And yeah. But again, in this, if you look at this mesoscale TCL file, it's still the same idea. And instead of calling Abacus or ISET, here we execute this command MATLAB. To let the MATLAB to run in the background, you need to use these options, no desktop and no splash, and to run this this file name.
Just a quick question. I might be wrong, but the last time that I cloned your repo, this example was not there. It was only the reference.
Oh yeah, I realized this morning is for this cantilever plate, I forgot to HG add these files. Yeah. But the T join, I think those are added. Yeah, I will check those. Yeah.
Yeah, that one.
Sorry about that.
Yeah, nice.
I see. Okay. So yeah, so basically here you run the MATLAB script in the background to call this MATLAB, to call this .m function, basically this one. And so the overall procedure is the same. And if this MATLAB solution is finished, and yeah, one thing I want to mention is that, so for MATLAB and ISET coupling, I think, so the convergence is checked inside the MATLAB script instead of in this TCL script. I kind of forgot the reason why I did that, but I think I had to do that for the shell coupling, or I had to do some debugging. So this way I can do some debugging easier. But I mean, so the convergence is checked in the MATLAB script. So this is the difference between this coupling, to the previous two cases.
Okay.
Yeah, I think down the road we need to do this check here, because instead of MATLAB, it will be Abacus, right, that you are going to use.
Yeah.
And then you cannot do the convergence check in Abacus.
Yeah, so if we take a look at this test.global plate IGL global.m, and so it get this global model, the file name is the global model, and it check the convergence at the beginning here. And everything else is just the code for shell solutions. Yeah, but in this mesoscale TCL file, and this is the only difference, and we're calling the MATLAB function, and we're not checking the residuals and convergence in this TCL. And this command is the same, and this, let's see. So you're doing the same procedure for the GFEM global local, and yeah, and all the IGL algorithm command are used the same way, but one thing, because I check, because the convergence is checked in the convergence check is performed in the MATLAB script, and also the acceleration is performed in the MATLAB script. In this compute residual .m MATLAB code. So basically,
but it could be done in TCL, right? If I put dynamic relaxation there in this TCL and commented those lines in MATLAB, do you think it would be the same thing?
I think because this acceleration, the beta is compute. Because this acceleration, I think, in this version of MATLAB code is computed based on the shell quantities. So that's why it is done in the MATLAB script.
I understand now.
Yeah.
Just a quick question. When you calculate the residual, are you using shell equivalent forces? I mean, because you have forces and moments, right? So are you, and then I think I saw that you do the dot product of the residual to get a single number. So I don't know, it's maybe it has nothing to do with the IGL method, but for me, it sounds like you are adding forces with moments, and I don't know.
Yeah, that's a good point. Would be better be the residual of the forces than the residual of the moments. Is that what you're saying, Javier?
Yes, or maybe, I don't know, do the conversion to nodal forces and then work with nodal forces only.
The moments to nodal forces.
Yeah, the moment to nodal forces.
Yeah, 3D, right? Let's say the moment in the shell, transform that in nodal forces for the solid.
Yes. I don't know, maybe it has no impact, but what I'm thinking right now is
I think I have tried. I think I have tried your idea, but I can't say for sure. I think I remember I have tried your idea, and it did not converge.
Okay.
At all. Yeah.
Okay.
Yeah. But maybe at that point, maybe there are some other bugs that ruining the convergence. In the future, maybe you can try that again. Yeah, but I mean, so for MATLAB ISET coupling, so the convergence check and the acceleration is done in this in the shell MATLAB code, and so here we don't specify any acceleration technique in the TCL, and we don't check convergence in the TCL, and we don't need to get the residual forces from the TCL.
Okay.
Yeah, and so the other process is the same.
Is there any reason for why in this example you set direct method for point Dirichlet? I saw you had that line uncommented in this example. In the previous ones, I don't think you had that. Yeah, this line. Maybe it was just testing, but
you can use it. Yeah, I'm just testing. You can use this true or false. Yeah.
Okay.
The nodes at the interface, they are all standard FEM nodes. So
yeah,
I think direct method is better.
Yeah, direct method is better.
Then the forces are going to be better because the displacement will be, let's say, exactly 0, exactly the value. And the forces, the reaction force will be more accurate.
Makes sense.
So at last, we need to take a look at this MATLAB global model, how to set this up. So this model is generated, I believe, from GID, because that MATLAB code works with GID, right? And so this is basically the file the GID generates if you draw a model there, and it will generate the material properties and the nodal coordinates and element connectivities and also the boundary conditions for the fixed nodes and point nodes. And this is the uniform distributed load, but these are basically zeros for this case. That you need to, I think it generates automatically, but I mean, so this size is basically the size of your problem. Yeah.
How many nodes you have?
Yeah.
Yeah.
Yeah, you have 15.
83 minus 18.
But there are 3 sections we need to add. One is this interface elements, which is so let me show this model to be better explain this. So basically this interface elements are these 5 elements here. So as I mentioned before, we only need to get the element list on the inside of this domain of interest. Right, so these are elements 3, 13, 23, 33, and 43. Okay, so this basically corresponds to those we set in Abacus in file and those in the global TCL file with the element list command. And then we also need to specify the interface nodes are these 6 nodes along this interface line. And then finally, we need to have this the corresponding solid node. So basically the nodes interface local. So these are the solids, the node IDs in the solid model that corresponds to this interface nodes. So basically this is 51 and 49 corresponding to, because we have a node up and below and above, and so we have 51 and 49 for this shell nodes number 4. And so they are basically the same idea, and 55, 53 for this shell node 15.
Is there an order when you specify those
so
nodes?
This is the
up,
so this is positive and negative based on your coordinate system.
Okay.
Because this one is easier, we can say up and down, but if you have the T-joint example, you also have those interface on the vertical plate, and it's in the positive y direction, I believe. Yeah.
Okay.
So positive and negative y direction, x direction, or z direction. Yeah, so this is how we set up this plate model. So everything before this is generated by GID, and we need to add these 3 sections of interface information. And so we run the problem the same way. We run this method scale TCL to the end, and it will. So after this simulation finished, for the GFEM global local, we have the VTU files, but for the MATFEM or the MATLAB, the shell model, we have these 2 solution files called .mesh and .res, which stands for results, I believe. And then to visualize this, so we can use GID to visualize this. And one thing, when I have time, I need to dig into that, because I remember I had also converted these 2 files into pair-view format because I have this visualization that combining the shell model and the solid model, but I mean, for now I couldn't find the script for now. So right now I can only show this in GID. But if I have time, I can see if I can find those. Or you can try to search for the GID to a pair-view converter. Maybe,
well, I mean,
maybe in GID you can output the file into Abacus format, and then I guess you can convert Abacus format into pair-view.
Well, we are going to move away from MATLAB, right? So MATLAB was just a stepping stone to understand how the method works with shells.
Yeah.
And so the first step, the next step would be to have shells in ISET, which Nathan already implemented part of it when he took the plates and shells course last year.
Okay.
And so then you'll be closer to what you have ISET, where one ISET model is shell and the other ISET model is solid. And that will allow us to have things more, let's say, consistent, and don't need to deal with let's say another language, MATLAB, another post-processing. And then the final step will be Abacus ISET with shells in Abacus, but we want first to use ISET because it's much more convenient.
I see.
And so
I
think if unless Nathan Javier has other ideas, but I would suggest that use MATLAB as it is, as a tool to compare with when you have, let's say, ISET as a reference, but not try to make it much better in terms of usability.
Yeah, that makes sense. Yeah, because it's kind of not quite rewarding to try to figure out how to convert these post-process files.
Yeah.
Yeah, but your idea of doing Abacus, generating the ODB and then converting works.
Yeah, that one I think is more, that's more useful because we always need that.
Yeah, but for now you can just visualize this .res file. So basically in GID you can open this .res file to utilize the shell solution, and in pair view you can open the solid part of the solution. Yeah.
Cool.
Okay, I guess this is. See, I think that's all I want to talk about for MATLAB and Abacus. Yeah, there's no other like procedural differences between this and the other two cases. Yeah.
Yeah, I think if you can share these files with Javier and Nathan, all the stuff that you show, then they can try to run by themselves. They already start that with the files journal dissertation, so they have some questions about that, but that would be, these are another set of files that they can use to get familiar. Now that we have the recording where we explain everything step by step, your files are very organized, very clean, so they did a great job. I think it's very nicely organized, and for somebody that's familiar with ISET, should not take long to understand. They are already familiar with IGL. I gave them your MATLAB IGL code to learn the algorithm, and now is to map that to ISET in this setting, this framework here.
So yeah, what they're planning to do is to run ISET and ISET with shell and solid coupling.
That should be one of the next steps, yes.
Okay, I see.
Because then we replace the ISET shell with Abacus shell.
I see.
We would not do that if Nita has not already implemented the shells in Abacus. But he did that last year, so it's Is that correct, Nathan?
Yeah, that's correct.
And you implement the same element, right? This QLL.
Yeah, QLL.
Yeah,
over 3 L's.
Q3Ls.
Yeah. Yeah, I don't think I implemented all the types of boundary conditions. So maybe something that we can tackle fast though. And maybe something that we can even, if Javier wants to get acquainted with the code, is something that he can take a look on how to do.
Yeah, another, I think, good exercise for you too would be to create another problem yourself and solve using this method. Be at first ISET, but then you see, okay, I need to deal with the interfaces, information, I need to deal with this and that. And then in that process, you can also, okay, this could be improved. Can we improve this? How? Because right now, Haoyang is giving everything ready to go for you, right? But if you have to create yourself, I think that's when you really learn, when you have to do yourself.
Agreed. Yeah,
it doesn't have to be a complicated problem. Could be just a cantilever beam, something simple, right? Some plate with a hole, something like that. Some as simple as possible.
Yeah.
Have to install.
Yeah, I remember when I started. When I started, I just used a very simple problem, just a bar with two different material properties in the mesoscale and global region. Yeah, so
like that. What's his name? That there's a report with an example with a bar and two materials by that guy from Europe. What's
Olivier Alix?
Olivier Alix, yes. He has this very nice example that converges in one iteration.
Yeah. But I think you did in 3D, right? 3D bar, 3D elements for a bar.
Yeah, it's a 3D bar. Yeah.
Yeah, Yeah, so that's a good example because that's easy to check if it's right or wrong because you should get the exact solution, right? So
yeah, that's easy to check. Yeah. Mm.
And again, you have to go through all the steps: the global model, the meso model, the interface data, and all these things.
Yeah.
And then along the way, you try to identify things that could be improved, like how to generate this interface data, and so on.
Mm-hmm. Yeah. Okay. I have like 2 questions for Haoyang from the examples I tried to run. Do you have time to quick questions, Haoyang?
Yeah. Go ahead.
Okay. Yeah. I might share my screen because I think it'll be easier for you to see what is happening. So I tried to run the plate with holes from your thesis. This is example 2 of chapter 5. This one. And this one has plasticity in it, and the plasticity is, I think, the mesoscale, the local scale. And what happened? I'm using that code that you uploaded to the workstation to false. And when I did that,
can you hear me?
Yes, we can. A little bit different now, but yeah.
Yeah, my AirPods died. When I'm setting the boundary conditions, you call this function set point Dirichlet BC. And it does so. It asks what the material type, and the material type is plus 3D, not LS 3D. And then I get this error exit in that problem, the plate with holes. And I don't know if you change something like plus 3D to make it work, if you remember.
I thought I have added the function there, but how?
Goes to this error exit here.
Yeah, I see what you're saying. So have you tried running without that? I have a different version of the code that I have added this. I thought I have dealt with this. Just need to add a different.
I think that it could be just like doing this.
Yeah.
And here putting this.
Yeah.
I think
it should be pretty straightforward to just to create it.
I thought of asking you. I don't know if you remember. So
yeah, it should be as easy as that.
Okay,
you can
so
see,
I'll try to do
you can
that.
try to
The other thing. Oh, there's this command parse set reduce order for integration that, at least in the code that you uploaded, it shows that it does not exist. I don't know if it is something that exists in the master of ISET, or it's something that
reduce the order for integration. I think it's definitely the master. It should be. It's not in the code I uploaded, right?
Okay. Yeah, the code that you sent it doesn't have that.
You can check them out. I think it's
So I search here in a fresh version of ISET, like the one with the master, this string, and I couldn't find anything.
Okay.
Or in the whole project, I'm searching here. So that's why I'm like, is that existing anywhere in any other code of yours, maybe? Because I couldn't find in the master.
Okay. There might be another version that uploaded in the share folder. I can check if that's there. I think there's a different change that I pushed to the code. Yeah. Now I'll make this note and check that. Yeah.
Sure. And if I understand this correctly,
so this is just save some computation resources to, yeah.
Cool. Yeah, these were the 2 questions I had. I'll try to change that. And Javier, do you have any questions based on your experiments?
We did have some like small errors with one matrix being singular. I don't know. I think you, Nathan, have those on the screen.
Something like this appeared when we run the p-joint.
Yeah, the code runs, but it keeps showing that error. I mean, I think it's a minor error because at the end of the day, it doesn't run. But
it runs, and
so that's the LEA pack message.
Yes.
Yeah.
Maybe you can show to, that's this.
Yeah, I remember I got that as well, but
okay.
I mean, and then I checked the solution. There's no, I don't see any issue with that, so I think I just ignore that one.
Okay. Yeah. That's fine.
Do you know where we are using MATLAB? I mean, sorry, LEA pack. Where is this FAC and solve?
Could it be something to extract SIFs?
No,
maybe because
for isotropic material, I don't think we do that. Only for the orthotropic.
For the breast thing, yeah.
Yeah.
And also, when I run these demo examples, I don't think I get that. Let's see.
It's gonna be hard to find.
So this, you get this which example you try to run?
Oh, could it be the inverse map for the hex?
Inverse.
Yeah, but if it's
Agent. Crack front mapping.
So this happened which example when you?
The T-joint.
That's the T-joint with the propagating crack.
Okay. I think it might have something to do with the propagation, because in the output of my static crack, I don't get this. Yeah. I don't get this error.
Okay.
Because for the propagation, the T-joint propagation, if you look at code, I think I need to change or disable some sanity checks or the printout functions. Because some of the function does not support the hexes. I don't know if there's some function in the crack propagation code that works, that does not work for hexes, that's calling this issue.
Okay.
But to do the crack propagation in the pet mesh.
Yeah.
Yeah. So that's why I think this is just it's not really a this is not really a issue. I think this is caused by some auxiliary function that does not, like, it's not part of a solution. It might be just part of the, like, when you check the crack, when you check the parameters or the characterizations for crack mesh. So that might invoke some functions to calling this.
Well, you extract SIFs in the mesoscale, which is a hex mesh, right?
Yeah, it's a hex mesh.
That could be happen there.
Yeah.
Because you use the crack mana just for extraction.
Mm.
And then you are not doing propagation, anything, but you need to go through the elements, through the crack front, find the element that contain, that could be there. That you use the crack just for SIF extraction.
Maybe
so you need
try to do the inverse mapping, it finds that singular, then it says like, okay, this is not the element I want when it was doing find element, no?
Yeah, so it would be good, I think, to find where is this coming. But my guess is this related to the SIF extraction. You can, it's a static problem, right? Let's say the one that Haoyang just showed.
The one I just showed, a static problem, is does not have this arrow.
Even when you extract in the mesoscale?
Yeah, even when I extract at the mesoscale.
Okay.
And they mentioned this, that it only happens for the crack propagation.
Okay.
Yeah.
Which you propagate in the mesoscale too, right?
Yeah, we propagate in the mesoscale.
Yes.
I think that's it. Yeah. Because you have to do that, no, when you're extracting with the DCM. You get a coordinate behind the crack front, you do find element of this guy, and to do find element, you have to do the inverse mapping.
Yes.
And then probably you'll get some crazy matrices that when you do fact and solve, it shows singular, but even though it shows singular, it probably just like returns false. And okay, this is not the element I want. So that's why it's not a problem.
Could be.
I can check, but
at least you can check.
Could be.
Yeah,
at least put in your list. That doesn't have to be something now, but put in your list because.
Of course.
Yeah, I'll share with you the static crack examples, and you can try that again to see if that happens on your side.
Yeah. Yeah, could be that is outside of the element, then you get the singular matrix. I don't know. When you try to find the element that contains the crack to front point. Okay, so was there any other error that you got, Javier?
No, that's all that I have. I was having a problem with the shell simulation, but now that Haoyang mentioned that the residual convergence is checked inside MATLAB, I would like to take a second look first.
Okay. Okay.
Yeah, besides that, no, I think that's all that I have.
Okay, so in terms of short-term tasks, I think is you and Nathan can continue studying these after what you learn from Haoyang, and in the meantime, Haoyang can send the material that he went over today, so you guys can play with it. Yeah, and then try to, again, small fix here and there in ISET, and then maybe create one problem from scratch. And maybe you guys can decide which one creates what.
Yeah, that will be really helpful.
Yeah. Not sure if it is better to merge with the current version before we do that. Because if we have any improvements, is it better to improve the old version or the already merged version?
Well, I will not make any improvement now, only make fixes like the one that this plasticity material that was missing, right? This.
Okay.
Just, I would only fix things now and then have everything working, because then if everything is working, let's say Haoyang's files from his dissertation, how everything is working, then you, after you do the merge, you can run them again to make sure that you still get the same results.
Okay. Okay. Yeah, that sounds good. Continue with the studying and try to run a problem with Abacus doing it all by ourselves.
Oh,
well,
by
you
the
can
way,
also start ISET all by yourself,
Oh yeah, I said
because you still need to generate this interface data. Right?
Mm-hmm. Okay.
And then when doing Abacus, the ultimate goal is to use Abacus, right? So we want to improve the user experience, let's say, when using Abacus ISET.
Mm-hmm.
ISET is just, again, for us to, as a stepping stone to get to the final one.
Mm-hmm. Sounds good.
All right.
Do we still have Abacus license on FA workstation right now, or
no, we don't? But we can. Create a small problem that you can use just a teaching license.
Yeah. Mm-hmm.
Whenever it's needed, I can ask Kevin to install.
Mm-hmm.
Mm-hmm.
Just to learn, you want to solve small problems anyway.
Mm-hmm. Okay.
All right.
Okay.
Anything else, Nathan and Javier?
That's all that I have. Thank you so much, Haoyang.
So
no problem.
Just curiosity before I let you go.
Mm-hmm.
So in your job, does anybody use the TCL or everybody use nowadays Python?
Yeah, pretty much. I think nowadays we use Java.
Oh, Java.
Yeah. I mean, so in our work, basically, a simulation can record a macro that is in Java, and then you can run that macro, which is the series of commands that drives the simulation. Yeah.
Mm-hmm. Because that's HyperMesh can do that, at least used to, that you create some model in HyperMesh, and then HyperMesh generate a TCL file of what you did in the GUI. So you don't need to go through the GUI over and over again to do the same thing. Then you just run the TCL file.
Yeah, we do the same. We pretty much do the same thing, but with Java.
Okay. Interesting. Okay. Do you use Abacus in your work or any other?
No, not really, because we have our own solver that is pretty much like a competitor to Abacus. Yeah.
Is it Star CCM? No.
Star CCM.
Yeah. Cool. I saw that Star CCM does a lot of Formula One simulations.
Yeah. We started as the CFD solver, but then we add some other capabilities like finite element and some other solution methods.
Nice. Yeah.